Hello and welcome to Crypto University. In today's series, we will do a crash course for Solidity. We will go through the most important topics of the Solidity programming language, like functions, value and reference types, and modifiers. And we will program our own functional smart contract. If you have heard about Ethereum and blockchain already, and you would like to program Solidity, this course is perfect for you. If you have never heard about blockchain yet, I would recommend you to watch an introduction course about blockchain. My name is Roger, instructor at Crypto University, and I hope you will enjoy this series.
So, welcome back with my browser and my screen. In this first video, we would like to go to Remix, that's an IDE for the browser, to program Solidity smart contracts. I would like to show you this IDE a little bit, what you can do there. And then we would like to start to program our own smart contract and see which components that such a smart contract normally has. I will search for Solidity Remix. And we have here the Remix Ethereum IDE, and we just open that. As I said, that's a browser application, so you can actually run or you can program your smart contracts within the browser in this file structure. You can compile it and you can also deploy it to productional blockchains. Let's go through these different tabs and let's see a little bit what we can do here. So in the File Explorer tab, we have actually all our project. We have all our files that we need for our smart contracts. So we have smart contracts itself, where are our smart contracts which we would like to develop. So they belong all into this contracts folder. We have scripts that could be deploy scripts, transaction scripts, like just kind of helper scripts that we need, for example, for deploy smart contracts or for running some transactions on the blockchain. We have a test folder where are all the integration and unit tests for our smart contracts, so where we would like to have standardized tests. We have a dependency folder where are all the dependencies installed which we need for our smart contracts. So for example, there is a dependency called OpenZeppelin, and these are standardized contracts which we can use within our contract, so we can install them and they go into this dependencies folder, and then we can use them within our contracts. That's about the File Explorer. When I go here to Solidity compiler, we can see we can choose our compiler version. So what does the compiler do? It just takes the Solidity file that we have programmed and it compiles them to bytecode. So it generates bytecode out of our file, and the bytecode is then the thing that will be deployed to the blockchain. So it's kind of the middleman between the file and then the bytecode. We can choose a compiler version. We have currently 0.820, which is the most recent one. We can also choose really old ones to one of the first, the 0.11, but normally we choose one of the most current versions. So I'm choosing 0.820 now. And now we could compile here our smart contracts. However, we don't have any smart contracts yet, so I cannot really do anything here. So let's go to the next tab. This is the Deploy and Run Transactions tab. Here we can deploy our smart contracts and we can play around with our smart contracts. So we can send transaction, we can read out values from the contract, from the deployed contract, and so on. The first thing is our environment, which we would like to use. For testing purpose, we have the Remix VM, that's a virtual machine. So that's actually a mocked blockchain within our browser. If we deploy smart contracts within the Remix VM, it will not be deployed to a real blockchain. It will just be deployed in a sandbox or in a virtual machine. We can see that we have some accounts available here, which all have 100 Ether balance available. These are not real accounts, these are just accounts within our virtual machine. And then we can actually here deploy our compiled contracts, but we don't have any compiled contract yet, so we cannot really deploy anything yet. What we have else here in the environment select, we have the Remix VM. We can also choose injected provider. That's actually injecting a provider directly to Remix. And currently I'm using MetaMask. So when I open the MetaMask extension, we see that's my wallet. So I have an account here. This AB4 account is connected to the Girly test network. And when I choose this option, I'm injecting this account to Remix. So you can see here, the account is AB4. That's exactly this account. And it has 0.23 Ether available. And when I deploy a new contract now, I will be interacting with this account and with this blockchain. So when I deploy a smart contract now, it will be deployed to the Girly test network using this account. What I can do, I can change to Ethereum mainnet now, and you can see here it changes to main, so it's connected to the main network. And if I had some Ethereum left here, it shows now that I have some Ethereum. That looks like a bug because I don't really have Ethereum on the Ethereum mainnet. Now it just updated, so I have 0 Ether left. But if I have Ether here and then deploy one contract, it will deploy directly to Ethereum mainnet. So that's actually the gateway that we can use to deploy our contracts to a productional blockchain. I will go back to Girly ETH, to Girly test network again, come back to Remix. So let's go to our contracts folder and let's create our first Solidity contract. Let's call it first contract.sol, and it opens up a new file. .sol is the ending for a file which is a Solidity file. So every smart contract that we develop is a Solidity file, is programmed in Solidity programming language. The first thing that we use in a Solidity file is the identifier. So which license that we would like to use. So I'm using, it's always starting with SPDX license identifier, and then you specify the license for your code that will follow. So under which license you deploy your code. I'm using the unlicensed identifier, so I don't really use any license for it. The second thing that we use is the Solidity compiler version that we would like to use for our smart contracts. This always starts with pragma, Solidity, and then the version of the Solidity compiler that we want to use. I would like to use only 0.8.20 and save that. And then after that, we actually specify our contract, which is the first contract, and then like that. So that's how we define our contract. And within this block here, we will program all the functionalities for our smart contract. If you are used with object-oriented programming language, this might look a little bit familiar to you. So contract looks a little bit like class and the class name. That's actually similar because you can imagine you have a contract itself, it's kind of a class. And then when you deploy one contract, so one instance of your contract to one blockchain, this is kind of an object. So it's kind of a singleton which you deploy to the blockchain, and then it has a state and so on. It's kind of similar to an object. And that there you can kind of make the transition to object-oriented programming language. So when we just save that, we can see that we have, it's already green here in the compiler. So the compiler already compiled automatically our smart contract. I can press here also, and we see that everything went everything went fine. So the compiler compiled our Solidity code well. And what we can do is now we can go to the deploy and run transaction tab. We can use the Remix virtual machine for now. we have a fully functional smart contract. It doesn't do anything because we didn't specify anything within the contract, but it's a valid contract, which doesn't do anything. So what we can do now is we can just choose the contract here in the compiled contracts drop down, and we say deploy. And what it does is it deploys our contract to the virtual environment. And here down we have now all our contracts deployed. So this is our first contract. It's deployed at this following address. I will just copy it, just show you for a second. This is an Ethereum address. At this address our contract is available now. So when we want to interact with our contract, we will interact with this address, so it's deployed there. Other than that, we will have here read and write functions which we can use to interact with our contract. However, currently we don't have any function available as our contract is just empty. What we can do now is to go to injected provider. So I'm connecting to the Girly test network with my account, and I will try to deploy this contract to Girly test network. So what we did before, it was just deploying into a sandbox. It didn't really exist anywhere, but now I'm connected to Girly, to a test blockchain, where we would like to deploy our contract. I call deploy. You see that here pops up one new transaction in MetaMask. That's the deploy transaction, which I need to sign to actually deploy the smart contract. Now we need to wait a little bit, and now it is already fine. So when the transaction is mined, the smart contract is deployed to the test network. And we can see here now it's deployed. We have again one new address, which is this one. And now we can go to a block explorer, Girly Ether scan, and we can check in the Ether scan, which is actually an index service which indexes everything that happens within a blockchain. It indexes every contract, every block, and you can find here everything from accounts to smart contracts to transactions. Each transaction you can find here. So we can paste in the address of our newly deployed smart contract. I go here, and what we can see, we have a new transaction that we signed from our AB4 account, which generated the new contract here at this address with this transaction 1 minute ago. Now we see that it's successfully deployed to the Girly test network. Let's come back to Remix and let's see if everything is fine here. So maybe we can do just a quick summary. So what did we do? We created our first smart contract. It doesn't have any functionality yet. We didn't program anything here, but it's a fully functional smart contract which we compiled using the Solidity compiler, and then we have deployed it first to the virtual machine, which is just a VM within our browser, and then using the injected provider to deploy our contract to the Girly test network. Then we have the Ether scan here where we can check our address, where is our contract deployed. Next, we will start to write some functionality within our smart contract. We will start to learn about Solidity, what we can do here to implement new functions, new functionality to our smart contract. So let's start to create functionality to our smart contract. We will start by data types, so types that we can use, for example, numbers, strings, addresses, and so on, which are supported by Solidity. For that, we create a new contract called datatypes.sol, and we just copy paste the license identifier and the Solidity version, and we call it contract data types. And we have our smart contract. So let's start with a first data type. We take uint8. Uint8 is an unsigned integer. So that means it's only positive. It doesn't have a sign. So it starts from 0 and it has 8 bits. So the size is 8 bits. That means 2 to the power of 8. So 256 different numbers we can show within a uint8 number. We call it public, that we can access it from outside of the contract. In general, we can access every data inside the contract because all is public, you know, it's in the blockchain, so it's all public. But using the public modifier, we can create a function, like kind of a getter function for this variable, so we can easily get it from outside. So we call it uint8, and now we put the name of our variable that we would like to have. So let's call it default uint8 and the semicolon. So that's it already. So we have created our first storage variable in our contract. So our contract now contains a uint8 variable. And when we go here, we compile it, and now we can just deploy this contract. We see the contract here, and now we have a getter function, so a call function that we can retrieve data from the blockchain. So we can read out this variable. Default uint8, when I press here, we see it's 0. So that's the default value of an unsigned integer. What I can do now, I can just set it to a number. Let's set it to 10. And when I just delete this deployed contract, and I redeploy the contract again, and when we call that, we see the number, the variable is now 10. So default uint8 is now 10. And in general, a uint8 variable, we can have 2 to the power of 8, and that's 256 different numbers. The max value is 2 to the power of 8 minus 1. Why minus 1? Because we have a value 0. So we start from 0, not from 1. That's why the maximum or the biggest value within a uint8 is 255. And we can see that by calling type uint8.max. This will return the largest number of a uint8. And let's just deploy that and see that this is correct. Yes, we see. The max number is 255. So now we can continue with more big integers or unsigned integers, uint16. So that always goes up with multiply by 2, so 8, 16, 32, and so on. So if we have a uint16, as you guessed already right, the default value of a uint16 is also 0. But if we take the maximum value of a uint16, what we will get is this number, and that's actually the same as 2 to the power of 16 minus 1. That's the maximum value. And this just continues now with uint32, uint64, and so on until uint256, where we can store 256 bits. And that's exactly the same as before. So we have a uint256 max, and that will be, as you will see, a really large integer, uint256, and you see that's this large number, that's the maximum number. We also have integers, so int 8, for example. They have a sign, so they can be negative. So an uint 8. Let's see when we say type int 8 dot max. Now you can try to guess what this actually could be. So default int, sorry, that's a mistake. You can guess how much this value should be. Let's check it. Default int 8, it's 127. The reason for that is we have a sign, and the sign of an integer takes 1 bit. So we only have 7 bits left. So we have 2 to the power of 7 minus 1, that's the max here. And that is 2 to the power of 7, that's 128, minus 1 is 127. However, of course, we have a minus, so we go from minus 127 to plus 127. So if we call here the min, let's just check that. The minimum value of such an integer, what do we get? Minus 128. So unsigned integer go from 0 to a max value, and integer go from minus to plus. And also we have an integer 256 and so on. So we have the same like sizes of bits for these data types. Let's continue with a new other data type, which is called address. Address is an Ethereum address which contains 64 characters of a hexadecimal style, so 0 to 9 plus A to F. And an address actually identifies a user in the blockchain or another smart contract. So this variable type is really, really important because we often want to integrate our contract with other contracts. So we need to have the addresses stored of another contract in the blockchain such that we can call it or such that we can interact with it. Or we want to store addresses of users if we want to track balances, for example, of different users. So we need to store their addresses. And this data type stores these addresses. So let's call it public default address. And let's just deploy it and let's see what is the default value of an address data type. It's the 0 address. So the address always starts with 0x, indicating that it's a hexadecimal string after that. And then we have 64 characters. And the default value is called the 0 address. So it's just all zeros. I can set this address to another value. For example, let's just take this deployed address of the current contract. Let's just set it to this value. We save it. We redeploy the contract. And when we check this variable, we can see that this new address is stored within the default address variable. Let's continue with a next data type called string. You should be familiar with a string. So that's just a string, an array of characters. And when we deploy it, we can see that the default string is an empty string, so it doesn't contain anything, but we can set it to just something that we would like. And I just redeploy and we have a new string, and we see that this was stored within the string variable, the default string variable. And the last value data type that we will see is the bool data type, which is a boolean true or false. So the default bool is just false. When we deploy it like that, it will be false, or we can set it to true. So these types, there are some couple of more types, but these are the absolutely most important types that we use normally in Solidity programming. And these are value data types because they contain a value. For example, this string or this number or this address. There are other kind of data types now, and we call them reference data types. Reference data types reference to another storage. So actually we have a reference, for example, a mapping or an array where we reference an index or an address or whatever to a value itself. So it doesn't really contain just a value, but it contains references. The most important reference type is a mapping. So a mapping maps a value to another one. For example, address to uint 256. So let's double D like that. So this actually says we have kind of a key value store. We have kind of a dictionary where we have an address, and with the address, with this key, we can access a value of this address. An example that we could do is user balance mapping. Let's call it like that. So what we would like to do is we want to map an address to a balance, so to uint 256. We want to say each address, each key has kind of a value. And now let's check what is inside this mapping. So let's redeploy our contract. Okay, I just need to save it first. We just redeploy it again. And now we see we have user balance mapping, and we can add an address as a parameter. So we can access for an address how much is his balance. So let's just check the balance of our deployer address, and the result default of course is 0 because we didn't set any balance. Next, let's just set a balance. For that we create a function. I will explain more about functions later on, so you can just imagine that's a function which we can call from outside, which will set the balance of this mapping or of an address. Set balance. We add a parameter address to uint 256 new balance external, and that's it. So what we can do now is we can say user balance mapping, so that's this mapping, and we can now access the to address. So we go to the address itself, we take this reference and we set there the value of the uint 256, so the new balance. So what we are doing is we can set for an address now a new balance. And let's redeploy our contract, and now we have this set balance function where we can put these parameters. So let's say for ourselves, for this address, we would like to set the balance to 100. We call transact. This function was executed, and this mapping was written. And now if we check the user balance, so if we check on this mapping now, the address for which we have just set the balance to 100, we can call that, and we see 100 is now stored within this mapping. If we choose another account, let's say this one, and we call that, it's 0. So for this one, the balance is 0. So we have successfully created a mapping now for an address and for a user balance. Of course, this function is not really intelligent because everyone can just call it and can set balances to other addresses. We will see later on how we will deal with that and how we will do that more securely. Let's continue with an array. So an array is a reference type in Solidity as well. We can, for example, create a uint 256 array. We call it public, user balances array, let's call it like that. And what is an array? Of course, an array is a list with an index. So each element in the list has an index. So it starts with 0, the 0 index, and so on. And we can request the values using the index, and that's our reference here. So in the mapping we have an address, or we have just some kind of value type that we would like to use, and in an array we use an index to request an element out of this list. So let's redeploy it and see how that looks. So we see here a user balance array. We can also call that with a uint 256, and that's the index. So we can start from 0. We can say what is at place 0 in the index, which element, which uint 256 is there. So let's call that, and we get an error because the array is empty. At index 0 there is any element, so we get kind of a reference error because there is any value attached at reference or index 0. We need to fill first the array. So currently the array looks kind of like that, like empty. What we can do now is we can set here the user balance array, and we can say push, which will push a new element to the array. It will just append a new element to the end of the array. And we can say new balance. We just push that to the array. Let's redeploy it. Let's see. We set a new balance again. Take the address and we say 100. Transaction complete. Again, the balance is set in the mapping, and now let's see in the array, we go to index 0, we call it, and at index 0 we have this element 100, which we just pushed into the array. If we go to index 1, we see we get an error again, because there is any element at index 1. The array has size of 1, so the array now looks kind of like that. Summing that up with the mapping and the array, so the mapping is a mapping between, or a reference between, a data type which we can choose to another value, and an array we can access the elements within the array using the index of the array. So let's continue with another thing that we can do in Solidity. We can actually create our own data type. So we can create a struct. With a struct we can kind of create like a class which we can use as a data type. So for example, we can call it user balance. So we can create this data type, and within that we can now specify new value types or reference types. So for example, I can say a user balance contains a uint 256 balance and a uint 256 updated at. So it always stores when the balance actually was updated. And now what we can do is we can create a new mapping which maps an address not directly to a uint 256 to just show the balance, but it maps it to a user balance. So an address maps to such a struct which contains a balance and an updated at. Let's call this mapping user balance mapping struct. And let's see how this works. So let's just deploy the contract. We have the user balance mapping struct. We call it with an address. And what is stored there? It's stored balance 0 updated at 0. So these are the default values from the uint which are used here in this struct, as we have not written anything within this mapping yet. Let's do that. We use the user balance mapping struct, and we would like to write into 2, so to this address that the user provided, and there we want a new user balance. It's kind of creating a new object out of a class from an object-oriented programming perspective. So we say the balance is the new balance, and the updated at is the block timestamp. We will see that later on what this is exactly, but this is actually the Unix timestamp in seconds when the block was mined. So that's the current timestamp, let's say, when the user called this function. Let's deploy our contract, and we set balance again. Let's set balance to 200, transact, and when we check the user balance mapping struct for this address, we can see that it doesn't do anything. Maybe I didn't, let me deploy that again. Maybe I didn't save the contract itself. Let's do that again. 2 with a value of 200, transact, and we check. Yeah, I forgot to save it. So we have now a balance of 200, and we have an updated add with such a Unix timestamp. Let's go here to Unix timestamp, and we just paste it here and see what is this timestamp. It's actually a few seconds ago, so it's correct. It just added the timestamp when I executed this transaction here up. So that's about the struct and this inside the mapping. We can also add a user balance array. So we can do exactly the same just for an array. User balances array struct. And we can also push a new user balance to an array. So what I can do now, I will just show you a little trick that I don't need to copy that. I can create here a new local variable. We call it a memory variable. This variable will only live within the function scope and not outside of it. So user balance, and I need to specify that that is a memory variable, because it should only live inside this function. It just helps me within the function. I create a user balance struct and I store it into this memory variable. And now I can just use this variable here to set it into the mapping. And also I can now say user balance array struct dot push, and we push the user balance. That's just that I have a little bit less code here, that I don't copy paste all of this logic. I save it in a memory variable, and then I use the variable to set the entries into the mapping and into the array. Let's save that. Let's redeploy. Set balance again. Let's set the balance to 100, transact, and when we go to the balance array struct and we go to index 0, so to the first element inside this struct, we can see that we get the same object or the same struct. That was it for the basic data structures in Solidity. We will continue now with operators used for uint and integers. So we have seen about variables and data types in the last section. Now let's check out what we can do, which operators we can use to do calculations, to compare values, and so on with Solidity. For that, I will create a new contract file. Let's call it operators.sol. As always, we copy the spdx identifier, the Pragma Solidity version, and we say contract operators. I will initialize some values first. A uint 256, let's make it public. let's call it A, and I set it to 5, u into 56 public B, and I set it to 2. So let's start with arithmetic operators. So the operators we know from our math class. Let's start with public sum. So how we can make a sum out of two values? We do A plus B. Really simple. And let's just check that. We compile the contract, we deploy it. A is 5, B is 2, and the sum is 7. So that's correct. Let's continue. We have the difference, and let's say that's A minus B. And let's take another difference, difference 2, B minus A. Now let's see what happens. So A minus B is 3, right? So that's completely fine. But let's check this one. B minus A is 2 minus 5. It should be minus 3, but we wanna assign it to an unsigned integer. So we are going out of bound. So let's see what happens when we wanna call this difference. To deploy it again. And what we see is we get already an error. The called function should be payable if send blah blah blah. That's not the correct error message. So we don't really get the correct error message, but we cannot deploy it because it want to execute this line of code, and it cannot, because it cannot assign this value to an unsigned integer. So let's do it as an integer, but then we have a problem because we have two unsigned integer that would result in an unsigned integer, and we cannot assign an unsigned integer like that to an integer. So what we need to do, we need to cast them to an integer itself. So we do an int and an int, and we kind of transform this 5 of an unsigned integer to an integer, and the same for B and for A. And then these are two integers, and we subtract one integer from the other, and we assign all of that to a new integer. So let's deploy it. I need to save it, deploy it. Now it works. And we check the difference too, and we see that's minus 3. The difference is 3. So all correct here. Let's continue with another one. The product. Really simple. A times B. And we have a quotient. That's A divided by B. And now another question. What is the result of that? We have two unsigned integers that we divide, and we assign it to another unsigned integer. So an integer doesn't have like a floating point. So 5 divided by 2 should be 2.5. However, assigning it to an integer just removes everything after the decimal. So 2.5 will just be 2. We can check that. I will save it. Let's deploy the contract again. And we see the product. 2 times 5 is 10, and the quotient is 5 divided by 2, 2.5, and we just remove everything after the decimal, and we get 2. What is more is we have a power, u into 256, power, that's just a and then 2 of stars, so 2 multiply of b, and that's actually to the power of, so a to the power of b, 5 to the power of 2. This should result in 25. Let's see that. Power 25. And we have another one, that's the modulo operator, that's the percentage operator. So the modulo is just the rest that you get when you divide one number by the other. So 5 divided by 2 is actually 2, and the rest 1. So you get 2 rest 1. And the modulo is just then the rest. So that's 1. Should result in 1. Correct. These were the arithmetic operators. And there is another type of important operators called the comparison operators. So what we actually do is we compare different values and it will return us a boolean, so true or false, if the statement is true or false. So let's call bool public is larger or equal. So we can say A is larger or equal to B. So this expression here, we will check, is A larger than B, larger or equal than B? 5 is larger or equal than 2. That's correct. So it will return true. Let's check that. We deploy the contract. And we see is larger or equal. I need to save it again. Just forgot about that. But now we have here is larger or equal. And the result is true. So there are now different of them. So is larger. A is larger than B, so that's a strict larger than. When they are equal, this will return false. We have a is lower or equal, so A is lower or equal to B. And of course we have the is lower, so the strictly is lower. A is strictly lower than B. Then we have an is equal. So we check if A is equal to B. And is not equal. Not equal. A is not equal to B. Let's check that. We deploy our contract. And we start from here is larger, so 5 is larger than 2. That should be true. True. A is smaller or equal to B. 5 is smaller or equal to 2. No, that's incorrect. So is lower or equal is false. Is strictly lower is false as well. A is equal to B. 5 is not equal to B, so that's false as well. Is not equal, so A, 5 is not equal to 2. That's true, so that should be correct. Is not equal is true. So these are the comparison operators, the most important ones that we use for check if some values, for check two different values. And then the third category are the logical operators. So these are kind of operators for Boolean values if you want to see if and, or, and so on. So let's initialize two Booleans, expression 1, and we say that is true. We have an expression 2, which is false. And now we have the AND operator, which is expression 1 and expression 2. So if both are true, this will result in true. If one of them is false, this will result in false because it requires both to be true. The OR operator is like this. It requires at least one of them to be true, and then OR will be true. So if expression 1 or expression 2 is true, the OR will be true. And we have the third one, which is not. So that's just not expression 1. And this will just negate this expression. So if it's true, it will be false. If it's false, it will be true. Let's deploy this contract again. And let's start with the AND. So expression 1, true and false. This will return in false because both need to be true, such that AND would be true. AND is false. Or expression 1, true or false, it will result in true because it requires only one to be true. Let's see, or is true. And not expression 1 is false because true, it was true, and now it's just false. Let's see, it's false. So these are the logical operators. And this was the section for our operators. We have arithmetic operators for our number value types. We have some comparison operators. We can also apply them to our number value types. And we have logical operators for Boolean values. There are more operators available, for example, bit operators, but we will not go into detail of them. These operators that we have here are the most common ones, and you need them in general for programming Solidity. If you don't have a really weird or a really special case in your smart contracts, you will not need any other operator. After the operators, we will start to talk about functions. In this part of the course, we will go a little bit through the structure of a Solidity smart contract, and we will go through the functions, how they look, what we can do with them, which different functions there are, and we will play around with them. So let's start again with a new contract. Let's call it functions.sol. Functions.sol, yes, correct. We copy the license identifier and the Solidity version, and we create a new contract, functions, compile it, and we are ready. So, first thing, we have seen that we have variables. For example, we have a string public some text variable, and we call them when they are on the level of the contract. So when they are just inside here, we call them storage variables. This means if we deploy a contract, so if we deploy this functions contract, we have exactly one public variable which is stored exactly once within the contract. So we can set this variable to some string, we can then modify it, and it will just be stored at this place. So it will be stored at one place. This is actually the storage of the contract. So this will be persisted within the blockchain. Another kind of variable is a memory variable, and these are variables within a function. So I create here a function, and we call it memory function, public, and now we create a memory variable, so string memory new text, and let's give it a value, for example, memory. So what we are doing here is this variable here only exists when we run the function. So when we run the memory function, within the function, this new text is available. It's only in memory. After the function is done, so when the function is run through, the memory, the new text variable will not be available anywhere anymore. Not like the storage variables, which are persisted on the contract. So what we can do now is we can say some text is equal to new text. And what we are doing is we just assign to some text this variable, and then it will be persisted within the contract. So that's important. We have two general types of variables. We have storage variable, which are here in the contract defined. Mostly they are on top of the contract. And we have memory variables, which are just defined within the scope of a function. Let's call that memory variable. What we have more? A smart contract always can have a constructor. A constructor is kind of a function which is executed when the smart contract is deployed. So it's exactly then executed, and it will never be executed anymore after that. So it is kind of an initializer of the smart contract. So what we can do, for example, in the constructor is we can say we set some text to, let's call it constructor. And this will be executed when we deploy the smart contract. So let's try that out. We compile the contract, let's save it again, and then we deploy the functions contract. Let's see. What is some text? It's constructor. So constructor was executed when I deployed the contract. That's again similar to an object-oriented programming language where you have a class and then you have a constructor for the class. So when you call new class, you generate a new object, and then the constructor is executed on the new statement. That's exactly the same here. When I deploy such a contract, the instance of the contract we execute the constructor first. And now let's see, when I call this memory function, let's call that. I will go through here, and we see it should change the new text storage variable, so the some text storage variable, to the new text, so to memory. Let's do that. Okay, it was successfully executed, and now some text is memory. So far, so good. So let's jump into real functions of Solidity. First, I would like to talk about visibility. So where are functions visible? Within our contract, outside of our contract, maybe both? The first that we will see is the seen from outside and inside the contract. That's the public function. So I call it public function, but what makes it public is when I write public. And let's set some text to public. So what happens here, when a function is public, I can call this function within the contract itself and also outside of the contract. So when I deploy it, let's do that. You can see the public function here that you can call from outside. When I call that and we see some text, it's public. So we executed this function successfully. However, I can also call the public function from within the contract. So I can call here public function on the constructor, for example. And what it does is it will, when I deploy the contract, it will call public function and it will set some text to public. So let's do that. Deployed some text public. Okay, that's the public modifier or visibility modifier here. We have another function which is internal. Normally internal functions we prefix them with such a dash, with a lower dash, such that we can immediately see that these are internal functions. Internal functions are only visible from inside the contract. We can also say and also from inherited. We didn't check inheritance yet, but we can also inherit other contracts, and they are visible within inherited contracts as well. Also public functions actually. So they are also from in contract. But they are not visible from outside of the contract. So let's say some text is internal. Let's redeploy our contract, and we see the internal function is not visible from outside. However, we can call it from inside. So let's call internal function here. Deploy the contract, I call the public function, it will call the internal function, and our variable is internal. So far so good. Next function is the private function. The private function is similar to the internal function, it's only visible from within the contract. But it's not visible to inherited contracts. So when I inherit functions contract in another contract, this private function will not be visible. And of course, from outside, we cannot see this function neither. So it's not here. The next function is the external function. The external function, as it already tells us, is only visible from outside and not from within. So I cannot go here and call the external function. So you see, this gives us an error, it's not found. So because we cannot call it as it's only externally available. That means if we deploy the contract, we have our external function here that we can call, and then it's set to external. These are the visibility modifiers for the functions. Next, we would like to see the return statement or the return type of the function. Return values. So let's say we have a function, let's call it return function. We make it public and we make it a view. That's another modifier that we will see after what this is. And it returns a string memory. And like that, we can make a return out of a function. And what we can do is we can say return, and we can give a string. So let's give the sum text. So we return the sum text from this function. So we can give something back. When we deploy the contract, we see the return function, I call it, and it returns the sum text variable. We can see that this is kind of blue here and not orange, and that's why it's a view function. It's not writing to the contract. We have seen these other functions, they are writing to the storage of the contract. So we need to do a transaction. We are changing the state of the blockchain because we are setting some text to a new value, and that's a transaction. And here we are just retrieving a value, we are just reading from the blockchain. That's actually here why we have a view, and that's why here we see it as a blue button. We just call it. You can see it also here. It says call from and when we call another of that, it says VM, and then we did actually a transaction. So we transacted. we sign the transaction and send it to the blockchain to change the state of the blockchain. Because now, when we call return, you see the value has changed. Okay, now let's talk about important modifiers of Solidity functions. One we have already seen, that's the view modifier. So the view modifier indicates us that within the contract or within the function, we don't change the state. So let's say I say some text is equal to blah blah. We see that here we get an error because it modifies the state. So function cannot be declared as view because the expression modifies the state. So that's not allowed within a view function. There is an even more extreme case, and that's the pure function. Let's make it public, and pure returns, let's return a uint 256. And the pure function is similar to a view function. It doesn't change the state, but even more, it doesn't read out the storage of the contract. So what we do here is we read out some text. That's a storage variable from our contract. And in a pure function, so when I say return some text, it will give us an error because it's not pure, it's just a view. We are return argument type string storage ref is not implicitly convertible. Sorry, that's another problem because we need to make it string here, of course, but then still we have an error, and this is because the expression reads from the environment or state and thus requires view. Let's make that back to uint 256. And a pure function can, for example, only return something like that. It doesn't read from the storage of the contract. Let's check that out. Let's deploy it for a moment. Let's see these functions. So we have here this pure function 15, and we have the return function, which returns us the some text. What is more is we have, of course, a write function. And a write function does not have any modifiers. So it's similar, or it's the same as all these above we have. So we are writing the state. We can set some text to write, and that's a write function. And to call such a function, we need to execute a transaction to the blockchain. And we see it again, it's an orange button here. So write function, we can see some text is now write. Another modifier is the payable. Public payable. And what payable does is we can send Ether, or the native currency of the blockchain, we can send it to such a function. When I say that, let's set some text to payable, deploy it, and we see that gets read here. When I say that, I mean the value. So we can send, maybe you saw that before, we always had a value of 0. We never sent any Ether to the contract. We only paid transaction fees. So that's why our account here has still 99 Ethers balance. We just paid a little bit for gas fees. But what we can do with a payable function, we can send an Ether value within this function. So we can, for example, say I want to send Ether, 1 Ether, and I can now call the payable function. We see that our account now has only 98 Ether, so we send 1 Ether to the contract, and this function accepted this 1 Ether. And we also see we have now a balance on our contract with 1 Ether. So with the payable, we can make the contract accessible for paying or sending Ether to it. These were the most important modifiers for Solidity functions, and let's see some other coding blocks which we can use in Solidity. So there is, for example, the if statement. Let's make that public pure returns Boolean. So we can say what I do here is I accept a parameter from the input, and what I do now is I say if. So if the input is, for example, let's say 10, I return true, and else if it's not equal to 10, I return false. Let's check this function. We delete again, we redeploy it. If function, and we can see we can have an input now here because we have a parameter that we can pass on to the function. And let's say 5, it's false because it goes inside. 5 is not equal to 10, so it goes into the else block and it will return false. If I enter exactly 10, it will be true because 10 is equal to 10, so it will return true. And we also have a for loop. Let's say loops. That's a public pure returns uint 256. And I will make a memory variable first, and I will say number of iterations, and I make it 0. So I set it to 0, and now there is a for loop, so I can say for uint 256 I equal to 0. So the initial value for a for loop, so I starts with 0. Then the condition when the loop should stop, I want the loop to stop, or I want the loop to be run as long as I is smaller than loops variable. And the updating statement, so what I want to do with I, every time I go inside a loop, I want to do I++, which is actually increase I by 1. So what it does is it starts with I0, it goes inside the loop, it executes the loop, comes back, it will check the statement here. If you have, for example, 5, I is 0, so 0 is smaller than 5, it goes inside, and every time it goes inside, it will increase I by 1, then I will be 1, then it will be 2, 3, 4, until it will be 4, and when it's 5, 5 will not be smaller than 5 anymore, so it will go out of the loop. What we do is we say number of iterations plus plus, so we increase this variable every time we enter the loop, and then we just return it, the number of iterations. Let's redeploy our contract, and we call the for loop, let's say 5. We call it, and our result is 5 because we went 5 times within the loop. So we went 5 times inside this loop, and we increased the number 5 times. That was it with the function section of this course. After, we will see a little bit more specific things about Solidity, like global variables, what we can use there, and we will write our own modifiers for functions, see a little bit about inheritance, and in the end, we will do our own contract combining all the stuff that we have learned so far. We will continue now with global variables. Global variables are variables which are exposed by Solidity, so we can use these variables within our contracts. For that, we will create a new contract in our Remix environment, and we call it global variables.sol. And as always, we copy the identifier and the Pragma Solidity version. We go to the compiler and we change to 820, so it will compile successfully. Let's create our contract. Let's call it global variables. And let's start with the first ones. I will start with a function and I call it block variables. Let's make it public and a view, and it returns two variables, so a uint 256 and another uint 256. Like that we can say how many or which variables are returned, and we can also specify multiple return values. So what I do is I return two variables, and this is the block timestamp and the block number. And you can see I didn't specify any variable block in our contract, so these are global variables which are always within a contract, which are always accessible within a contract. So when I call this function block variables, it will return me the timestamp and the number at the time of the execution of the function. Let's see, we compile our contract, and then we deploy our global variables contract. And now when I call this function, we can see the first value is the timestamp. Let's go to check that, Unix timestamp. That was a few seconds ago. So the Unix timestamp is returned by block.timestamp, and block.number returns us the height of the blockchain, so the current block number of the blockchain. And as we are working in a virtual machine, this is just 2. So because here the blockchain always gets redeployed, let's say like that, and it starts with block number 1 all the time. But of course, when we are, for example, on Ethereum mainnet, let's go to Etherscan, we can see that the current block height or the current block number is around this number currently. So when we call the function and the contract would be deployed on Ethereum mainnet, we would get something like that as a block number. So these variables, we can take use of them within our contract. Often that's used for example, for vesting contracts, meaning when you have a token and you want to give this token to many people, but these people cannot request all the token at once. And then you can use, like for example, block timestamp or block number to calculate how many tokens they can vest at the current time. So yeah, that's two really important numbers. So the next that we would like to look at is the message variable. So I create a new function, message variables. We make it public and we make it payable. For that, we also create two storage variables, an address, call it sender, and an uint 256, and we call it value. And now when somebody calls the message variables function, we set the sender to the message sender. And that's a global variable, this message and the sender. This will return us the sender who called or who transacted with the message variables function. And we can get the value by calling message value. So that's the value the sender sent to this function. I save it and we deploy our contract. We see we have now the message variables function, the sender and the value is 0. And now we call that function. Let's put a value of 100 way, and we call it with the contract or with account 5b3. So message variables, we call it. And now when we check the sender, we can see that it's the 5b3 account which called this function, and the value is set to 100 which was the message value. What more that we would like to look at is the require statement. So we create a new function, it's a public view, and it returns a Boolean. A require statement is a statement where we can check if a condition should be true. If it's false, we revert, so we give back an error such that the function does not continue to be run. So we use this require statement, and then we can add a condition. So let's use our message sender, and we would like this message sender to be the sender. So to be this variable here, this storage variable. Otherwise, we return an error and we say this can only be called by the sender of message variables. And if it passes this require statement, we just return true, as we return a Boolean. So let's redeploy our contract. We can call this require statement. So bear in mind, the sender is the 0 address. We didn't call message variables yet. And our message sender is the 5-bit tree. So when we go into the require statement function, the message sender will be 5-bit tree and the sender will be 0 address. So this require statement will be false. So we will return this error. Let's call it require statement, and we see it reverted. Go to the error, it say this can only be called by the sender of message variables. So what we do, we call message variables. Let's call it with 100 way. It went through, and now when we check the sender, we can see, okay, now it's this variable. We also have this value. And now when we call require statement, the message sender, so this address will be the same like the storage variable sender, and it should go through the require statement. So let's call it, and we see it returns true. So we passed the require statement. If we use another account now, let's take the second one here, the AB8 account, and we call require statement, we see the call reverts again, and it says this can only be called by the sender of the message variables. The last variable that we would like to look at is the this variable. So I create another function, this variable, and let's make it a public view, and it returns an address. The this variable returns us this contract. So it returns us the current contract, the global variables contract which is deployed. So what we can do is we can say address of this, and this is the global variables contract, and the address statement or global function will return us the address of this contract. So it will return us the address of the deployed contract. And just let's return that. And we save it, and when we redeploy it, we call this variable, and we see that's now an address. It's A13. That's the address where our contract is deployed. And we can see that here from the deployed contract, it was deployed at A13. So that's the exact same address like here. Like that, we can just access the address of our own contract. That's required quite often as well. For example, when we want to transfer from a token from an account to us, so to our contract, if we want to transfer a token from an account to our deployed contract, we use the address this to actually access our address to who we would like to send the token. With that, these were the most important global variables for Solidity. There are more, of course, but these are the most common ones that we usually use. Next, we will go through our own modifiers. So we will write own modifiers for functions. If we come back to another contract that we have lately developed, the functions.sol contract, we see that we have used many modifiers. For example, the view, the pure, the payable, and so on, different modifiers. So what they're actually doing is they surround a function with more functionality. So it specifies what we should do before the function and what we should do after the function. And what we can do now is we can write our own modifiers and add them to the functions. Let's start with a new contract again. So we call it modifiers.sol. Again, we copy the identifier, the Solidity version, and we create a contract, modifiers. I'll save it. And let's start now with a normal function. We have a function and we call set important value. We pass in a uint256 with a new value, and we make that just public. We create a storage variable, which is a uint256 public, and we call it important value. And what we do inside this function, it's just we set important value, the storage variable on our contract, to the new value that we would like to specify within this function. We deploy our contract, the modifiers contract, and now we see the important value is 0, the default value, and we just change it to 100 and we transact with this function, and now the important value is 100. So far so good. So now I can use any account that I would like. So I can use the third account here. I can set the important variable to 200 now, and that always works fine. So what we would like to do is we would like to add access control to this function. So we want that only the deployer of the contract can change this important value and not just everyone, because now everyone can just call that function and set the new value to the important value to a new value. For that, we will create a new modifier. So a modifier, we use the modifier keyword, and we call our modifier only owner. And now we have something similar like a function here. So we can specify what we would like to execute before the function and what we would like to execute after the function. When we use access control, and in many other cases, we would like to check something before we execute the function. So what we do is we use the require statement. So we would like to require that the message sender is equal to some owner of the contract. So let's create a new storage variable, address public owner, and we would like that the message sender is the same as this owner variable. If not, we say caller is not owner, so we revert the function. And what we do now is we just put such a lower dash, and what this will tell is execute the function. So we require before the function call, and then we execute the function. What we could do now, we could add something here after the function code. Let's call it like that. And this all before is before function code. And what we can do now is we can use this modifier here on this function. So we can say we want the only owner modifier. And what it does when we call set important value, it will use this modifier. So it will first execute the require statement, and then we'll execute the function. So then it will execute this line of code, which sets the important value to a new value. So let's deploy this code. And when we want to set now the important value, we always get a revert because it says the caller is not the owner. So let's check the owner. The owner is the 0 address. So what we need to do now is we would like to set the deployer to the owner variable. And we can do that by using the constructor. So let's add a constructor. This will be executed when we deploy the contract. So what we would like is we would like to set the owner to the message sender. So the account which deploys the contract will be set as an owner, and then this will be the only account which is allowed to set the important variable. So let's delete it again. I will choose here the first account, 5b3. And with this one, I deploy the modifiers contract. If I check the owner, we see it's 5b3. And if I set the important value to 100, it goes through because I'm using the right account. The important value is set to 100. If I change now the account to the second one, which is not an owner of the contract, and I set important variable, we get an error which says caller is not the owner. That's one thing we can do with a modifier. Something else that we can do with a modifier is we can pass parameters to the modifier itself. So let's check that out as well. We create a new modifier and let's call it max 100. And as like that, we can pass on a parameter to the modifier. uint256, I say I want to pass a value. And then we require that the value is smaller or equal to 100. So we don't want any value to be larger than 100. If not, we say max value is 100. And like before, we need to say that we would like to execute the function afterwards. And now we can just add this modifier max 100 and we pass on a parameter, and that's the new value. So the user which sends a new value, this will be passed on to the modifier and it will be checked if this value is actually smaller or equal to 100. Let's redeploy our contract. We set the value to, let's say, 50, and it passes. The important value is set to 50. Let's put it 100. It works as well. And let's put 101 now. And we see that it works as well, because I didn't save the contract. So let's deploy it again. Let's set it again to 50. That works. Let's set it to 101. And now we get this error which says max value is 100. So 101 is not allowed and the important value is not updated. These were own written modifiers. Often we use them for access control to check if somebody is allowed to call a function. Like here, we can also use more fine-grained access control, for example with roles. So we allow some accounts to call some functions, some other accounts to call some other functions, and so on. Next, we will go to events. Next, we would like to talk about events. Events are a feature of EVM-based blockchains, and we can write down some logs from smart contracts. These logs are not stored in the storage of the contract, so they cannot be accessed by other contracts. However, they can be accessed from outside of the blockchain. So in most cases we do that such that we can track, for example, transfers of tokens of a user, so that we can kind of track data from the blockchain easily from outside of the blockchain, for example, using a front end or a back end. For that, we create a new contract again. Let's call it events.sol. And again, we just copy the license and the Solidity version, and we make a new contract, events. And now we specify an event. So we use the event keyword followed by the name of the event. Let's make a new event called deposited. And then we can add some arguments to this event. So let's put an address, color, and the uint 256 with a value. And now we have defined a new event. Now when we call a function, we can emit this event, so we can store this event. Let's make a new function calling deposit, which is a public payable function. And the user can call this function using a value. And what we do, we just log an event which will tell us which user deposited how much. For that, we use the emit keyword followed by the event name, so deposited. And then we need to say a caller, so let's make it message sender, and the value, let's make it message value. And then an event is written on deposit. What we can do more is here we have an address caller. We can put here an indexed keyword. This will allow us afterwards to query the logs using the indexed caller, so we can filter by a specific caller. Let's say one account calls this function 5 times, so it will be written 5 times the deposited event for this account. And now when this is indexed, we can easily filter by this account and get these 5 events of this account. For example, maybe we want to sum up all the deposits of this user. So 5 times we will get 5 of these events, and we just sum up all the values, and then we have the total deposit of such a user. So let's save that and let's deploy this events contract. So we have a deposit function. I will add 100 way to the value. So this user is sending 100 way to this function. It went through. And when we go here to see a little bit more into detail of this transaction, we can see that we have here logs that were written, and we see these logs are an event called deposited with some arguments, which has a caller. This is this AB8 account, and with a value 100. So this is now stored in the events or in the logs. As I said before, events are often used to track transactions from users. For example, in ERC20 tokens, so in fungible tokens, we have a transfer event to see who transferred to whom how many tokens. And like that, we can track how many holders we have in an ERC20 token and so on. So the last element that we would like to discuss in this crash course is inheritance. So if I have a parent contract and a child contract, how do I copy code from the parent contract to the child contract? So how do I inherit functionality and code from the parent to a child? For that, we will start with a new file, which is called inheritance.sol. We copy all the identifier and the Solidity version. And now we create a new contract, and we call it car. And what we do with this contract, we add another key. So we add abstract to the beginning. What this does is it makes our contract abstract. Abstract means we cannot deploy this contract by itself, but we can inherit the code to another contract. So this contract is kind of, as it's abstract, we cannot create an instance of such a contract, but we can inherit it. So a car is abstract, there will never be a car contract, but we would like to inherit some functionality from car to more specific contract types. Let's say a car has a string public name and it has a function drive, which is public, pure, and it returns a string memory. And we return, we say it drives normal, drive normal. So it returns such a string. And now if we would like to deploy this car contract, we get an error and it tells us that our contract is abstract. So we cannot deploy this contract by itself. What we can do, however, is we can make a new contract, which is called a sports car. And then we use the is keyword to inherit the car contract. So what we are doing with this is we are copying this functionality to the sports car contract. If we save that, and now we go here to the contract drop down, we see the sports car contract. So let's choose the sports car contract and we deploy it, and we see that we successfully deployed a sports car. And when we open the contract here, we see we have a drive method and we have a name which we can retrieve. So the name is just an empty string because we didn't set anything. And when we call drive, it will say drive normal, which was inherited from the abstract contract car. What we can do now is we would like to override this default method drive in sports car. So a sports car doesn't drive normal, it drives fast, for example. So we would like to override this function from the base contract in our sports car contract. For that, this function needs to be virtual. So that's another modifier which tells us that we expect the client or the child contract to override this function for his needs. So what we can do now is we can say we have a function drive public pure returns string memory, and again returns. And now we see there is an error because this is already defined here. So what we need is we need to override keyword or modifier such that Solidity knows that if a sports car calls drive, it needs to override this function with this new function that we implement here. So in this new function, we return drive fast. And if we just deploy this contract, oops, that's the car contract, we want the sports car contract, of course, and we call drive, we see it drives fast. So it returns this one, and it was overridden. This function was overridden by this one. We also have a name of the car. This is still empty. So what we can do on the sports car, we can create a constructor, and we can just say the name is a sports car. So we can set the public variable from the abstract contract within this contract of sports car. As we copy this functionality to sports car, we can set the name of the sports car. And as we deploy that, we see that the name now is sports car. Let's create another contract, and that will be a standard car. And this also inherits the car abstract contract. We add a constructor and we say the name is a standard car, and we don't override anything. We want just the default implementation of the car contract. And we save that, and then we can see we have a standard car that we can deploy. And the standard car drives normal because it takes this function from the abstract contract, which we didn't override here, and the name is standard car, which we specified in the constructor while deploying the contract. This was a little bit about inheritance. So important, we have abstract contracts which we cannot deploy directly, but we can inherit in other normal contracts. So we can kind of copy the code from here to here, and that is often used with some standard contracts. For example, Open Zeppelin contracts, they implement standard implementation of well-known contracts, for example NFTs or ERC20 tokens. So what we can do, we have an abstract contract from there, and we can inherit them into our contracts such that we can use these standard functionalities from Open Zeppelin, and we can override some functionality if we would like, or we can just take the standard implementation. With that, let's continue with our whole contract, combining all the features and things that we have learned so far. So stay tuned for the last module of this course. Welcome to the last part of this course, where we will implement our own contract, combining all the stuff that we have learned so far. So we will do a wallet contract, which allows user to deposit and withdraw Ether, and the contract tracks the deposits of each user such that nobody can steal from another user his funds. For that, we start with a new contract, of course, which we call simple wallet.sol. We add, of course, again the Solidity version and the license identifier, and we create a new contract which is called simple wallet. So let's start with a struct, so with a data type for a user. So what we want is we want that users can deposit and withdraw, and we want to keep track of the user's deposits. So we make a struct for user wallet, where will be stored the user deposits. So it has a uint 256 with balance, and it has a uint 256 with last updated. Now we need a mapping. So we want to store an address, a user address, and such a user wallet. So a mapping between these two things. So when we request a user address, we would like to know how much this user has deposited and when was his last deposit. So let's create a mapping which maps an address, so a user address, to his user wallet. And we call it, that's user wallets. Now we can start to create our deposit and our withdraw function. Let's start with the deposit function. This is an external payable function, so it can only be executed from externally, and it's payable, so a user can send Ether to this function. We require such that the message value is larger than 0. So you must send some Ether. Otherwise, you cannot deposit 0. And now what we will do is we will update our user mapping. So we want to store if or how much the user has deposited. So what we can do is we say user wallets at message sender. So we get the user wallet of the message sender of the deposit function, and we say the balance we increase plus equal. That's a shortcut for increasing the value. So plus equal means the same. I will show you after. Plus equal message value. So plus equal is the same as that. User wallet equals the user wallet balance plus the message value. So it increases the balance by message value. And we also say user wallets at message sender, the last updated, we set that to block timestamp. That's the current timestamp when it was updated. And the ether that he has sent, this message value, that's already in the contract as the contract or the function is payable. So what we are doing, we are tracking now the wallet, the deposit of the user. That's for the deposit function. Let's make a withdraw function. And the user can now specify an amount, what he would like to withdraw. We make that external. And we start with some require statements. So require the user wallets of the message sender dot balance needs to be larger or equal the amount that he would like to withdraw. Otherwise, he doesn't have enough deposited for himself. So if that fails, we can say user has less deposited. Also, we can require that the address this dot balance, that's the ether balance. So you can remember address this, that's the address of the deployed contract. Dot balance, it will give us the ether balance of our deployed contract. So this needs to be larger or equal than the amount as well. Otherwise, we don't have enough ether on the contract itself to send to the user. So contract does not contain enough ether. And then we can start to subtract the value from the user's wallet. So user wallets of message sender minus equal, so we reduce it by the amount dot balance, of course. We reduce it by the amount. We know this cannot be lower than 0 because we have this check here that the balance needs to be larger or equal to the amount. So we know this is 0 or larger than 0. We also say the user wallets message sender dot last updated. We set equal to block dot timestamp, so the current block timestamp. And now the last thing that we need to do is we need to send the ether to the user, right? So right now we just subtracted the balance, the amount that he wants to withdraw from the balance and so on. We updated the storage variables, but now we need to actually send the ether to the user. We do that with message sender dot call, and we give a value which is the amount that we want to send to the message sender. This will return us two return values, a boolean sent and some bytecode, we would like to see if this boolean send, if this is true or false. So if it's false, it didn't work. So we require that send is true. Otherwise, we can say failed to send ether. And this call will send the amount to the message sender, which is the one that has called withdraw. So far so good. Another function that we would like is a view function. We want to get the user wallet by the address of the user so that the user can check his balance from the contract. We make that external, a view, and we say that returns a user wallet memory. So we return such a struct by this function. And we just say return user wallets at the user address. And that will give us back one user wallet for this address, so we can see the balance and the last updated of this user. Let's deploy this contract. So we deploy our simple wallet contract. It deployed successfully. I will use here the first account, the 5B3 account. I would like to deposit, let's say I will deposit 1 ether. We can see that this worked fine. The balance of the contract went up to 1 ether. And when I get the user wallet of this address, so I copy this address to the user wallet, get user wallet function. So we can see that we have the deposit amount of the user and the last updated timestamp of this user. Now we can withdraw some amount again. So as I added 1 ether, you can see we have many zeros here. So we have actually 18 zeros. So I would like to withdraw half a ether. So I put 17 zero, a 5 and 17 zeros. 17, and I call withdraw. And now you can check the balance of the contract is 1 ether, and the balance of the account is 98.99. And when we withdraw, we see it's 99.5 around. So we got half a ether, and the balance of the contract went down by half a ether. When we call the get user wallet, we see only half a ether is still deposited for this user. And let's say I add here a 0, so we want to withdraw too much. We get a revert message which says user has, user has less deposited. Now we can also use another account. So let's say this one. We can check the balance of this account. So let's copy the address. Let's add it here. And we see he didn't deposit anything. He can now also add 1 ether to the contract, or let's say 2 ether. He deposits that, went fine. We have now 2.5 ether totally deposited within the contract. But for this user, he get 2 ether. So let's say he would like to withdraw 2.5 ether. We get a revert message that he has not deposited that much, but if he would like to withdraw exactly 2 ether, that works fine, and he has withdrawn everything again. His balance is 0, and he has a last updated timestamp here. Let's come back to the contract and let's add some little features to this contract. So the first thing that I would like to do is I would like to emit some events. So we have an event on deposited, which has an address indexed user, and we have a uint to 56 amount, and we have another event withdrawn, which has an address indexed user and a uint to 56 amount. And now we can just emit here the deposited event with the message sender and with the message value as an amount. And down here we can emit the withdrawn event using the message sender again and the amount that he has withdrawn, so the amount variable. Like that, we have events on our contract as well. What we can do more is we can add a modifier, and let's make a modifier which checks the balance of the user if he has actually enough deposited for his withdrawn. So we make a modifier called check balance with an amount as a parameter, and what we do is we add these two require statements here, and after that we just continue with the function itself. So the amount, we have here an amount, I would just put a lower dash here as well, so that's fine here. And now what we can do is we can add this modifier to the withdraw function, check balance, using the amount from this parameter. So we pass it on to the modifier and we check the balance in this modifier. One last thing that I would like to mention here is this withdraw function. There is actually a thing that we can do wrong here in this function. What we are doing is we are first subtracting the amount from the balance of the user, and then we are sending the ether to the user. If we did that in the opposite direction, let's say we first sent the ether to the user and then subtracted his balance, we would have a vulnerability within our contract. That's called a re-entrancy vulnerability. So the problem that we have is that somebody could re-enter our function and drain our function or our contract for all the ETH that are within it. You can imagine if we call this function, so we send ether to the user, the message sender is an external account, or it can also be a contract. So it can also be a contract which calls our contract. And within a contract, you can specify when you get ether like this call, what you would like to do. So what you can do now is you can make a loop. When you receive the ether, let's say you receive half a ether, you can start to do a loop and re-enter the withdraw function. What will happen? We will call again this function and he can withdraw again the money, and that he can repeat in a loop until our contract is empty of ether. The reason for that happening is that we didn't update the user balance yet, so he can make a loop before we update the user balance. That's why it's really important that we first update the user balance with the amount and then send the ether to the user. Because like that he can re-enter the function, but his user balance is already updated, because it was already subtracted from the balance, the amount. So he cannot drain our contract without updating the balance storage variable of his deposit. Like that, we have a fully functional and secure contract. People can deposit ether within it, they can withdraw it, and we have a functionality where we check the balance of each user. So with that, let's deploy our contract again. We will deposit some ether to the contract. So let's deposit 2 ether to the contract. We see now 2 ether are inside the contract. The user itself has 2 ether deposited, and he can withdraw, let's say, 1 ether. $18.0, we transact, and we get the ethers back. We can also see the withdraw call emitted an event, which is called withdrawn with all the values that we have specified. And like that, we have a fully functional contract. So this was the last element of this course. It's a contract combining all the stuff that we have learned so far. I hope you have learned a lot within these 2 hours now. Of course, there are many more topics that we should discuss about, but for this crash course, I think you know now the most important and most basic things about Solidity. You know how to create a contract, you know how to deploy it, and you know the most important syntax for it. So thank you again and have a great day.